lecture about dispersive media. So last time we had updated equations. So from these three continuous equations, we derive these updated equations. Actually, this last equation, the integral, is equal to this due to nullity, and actually this is this is causality. And the last expression is due to the assumption that E field is 0 when the time is less than 0. Equation 1, and this is equation 2. And last time I said that this equation 2 requires the entire history of the E field to evaluate. But at the same time, the equation 2 requires also the knowledge of the epsilon for all time. So to evaluate the equation 2, we need to know this, the epsilon as a function of time. For that, we consider the Fourier transform of equation 1. So I simply Fourier transform the equation 1 here to get this. So actually people have measured this epsilon as a function of frequency by framing and tabulated epsilon as a function of frequency. So people have measured. They measured this epsilon as a function of frequency and tabulated them in various books and papers. So the bottom line is that if you know the analytic form of epsilon as a function of omega, you can inverse Fourier transform in time to get epsilon as a function of time to evaluate this epsilon at time steps, various time steps. So, you know, So, is there any questions up to this point?
Can I ask a question?
Sure.
Can we define this epsilon in numerical distance? We define it in a certain data range.
Right.
So, but this integration runs from minus infinity to plus.
That's correct, but because we are using the frequency range you are interested in contains the frequency range of the source. So when you excite a source, it contains only the frequency range in which you have the values here, values of S1. So outside those frequency, the current and E field are all 0, so it doesn't matter. That's a very good question. So we need to know the analytic form of epsilon of omega, and that So we have the tabulated data of epsilon of omega, and you can obtain the analytic form of epsilon of omega by fitting the tabulated data to the so-called Lorentz model, which is this is the Lorentz model, and you have these various fitting parameters: epsilon infinity, f omega pi, omega 0I, and gamma I. They are all fitting parameters. So when you have the tabulated and experimentally measured epsilon of omega, you fit those parameters to this analytic form to obtain these fitting parameters. And once you get these fitting parameters, actually you can inverse Fourier transform the Lorentz model. So So this Lorentz model can be inverse Fourier transformed analytically, and then you can evaluate epsilon as a function of time. So that's how we use the updated equations for the dispersed media. And actually, this Lorentz model is not the only analytic function to fit to.
So the capital N there is also a fitting parameter?
Yeah, you can use any number of fitting parameters, but I mean you can choose n, so that so by putting more terms, you can get more accurate fit. But at the same time, evaluating epsilon as a function of time takes a bit longer. So there is a trade-off. And this Lorentz model is not the only analytic function used to fit the tabulated data. example, numerical use something different. It uses so-called multi-coefficient. Material. Model. However, they say it is proprietary. They don't release what's the form of the analytic function they use. Yes.
So as long as you are restricting the field frequencies that you are concerned with, or your within the range of frequencies that you have empirical data for, why not just use like a really high order polynomial?
Yeah, you can do that. You can do that. But this is physics based, so there's a physical reason why the epsilon has this form.
Right. So you have to worry about like how many poles should you have.
Right. So I guess this MCM that is used in numerical is probably something like that. Yeah. But at the same time, you should know the analytic function should have inverse spread transform, analytic form of inverse spread transform. Yeah. So that's probably the only restriction. So this is the end of my lecture today. Is there any question? Otherwise, I believe John will continue to talk about mean scattering field. If you have any questions about FDTD, I'll keep coming to the lectures, so you can ask questions to me. Also, I'll teach one more FDTD lecture on scattering after John finishes mean scattering field.